Section 6.11 Equilibrium involving ideal gases and solid or liquid phases. In short, the Gibbs energy of a solid or liquid does not depend on pressure because their molar volume is very small. So first, let's look at this example. This is decomposition of solid calcium carbonate into calcium oxide and CO2 gas. So first, the Gibbs energy of this reaction is the Gibbs energy of formation of the products minus the Gibbs energy of formation of the reactants. Therefore, we write out this Gibbs energy of the reaction as the Gibbs energy of formation of CaO, calcium oxide, CO2, and then minus this reactant, calcium carbonate. And then this is very important. If pressure changes, the Gibbs energy of formation of a solid doesn't change. Well, it does actually, because dG equals negative SdT plus VdP. So there's a VdP term. So delta G is the integral of VdP. However, the volume of solids and liquids are so small that usually they are negligible. So that's why we put a approximate equal sign here and here for the solids. And then we just need to look at the pressure dependence of the Gibbs energy of CO2 here. So that's why when pressure changes, we have only this part involving this RT times the logarithm of PCO2 over P naught. Again, this equation depends on this dG equals VdP equation at a constant temperature. When dG equals VdP, for ideal gases, dG equals nRT over PdP. And then we integrate both sides. And then we learn that the Gibbs energy of formation of CO2 does depend on pressure in this manner. Again, for solids, well, again, the molar volume of solids or liquids is so much smaller than the molar volume of the gas. Therefore, if there's any correction, they will be much smaller than this term. Therefore, the corrections for CaO or for calcium carbonate is negligible. At equilibrium, we say this part is 0. Therefore, the right-hand side of the equation is 0. So we're writing this here. So this the whole thing is 0. And then we can write out the equilibrium constant for this reaction. First, we'll put this guy on one side, everything else on the other side. And then if we look at this three terms together, it's just the Gibbs energy of the reaction in the standard state, or the standard Gibbs energy of the reaction. And therefore, we have this term is equal to negative standard Gibbs energy of the reaction. And then we have this logarithm of PCO2, the pressure of CO2 over P naught at equilibrium is equal to negative delta G of R in the standard state over RT. And this is simply Ln/Kp. So the equilibrium constant is the pressure of CO2 over P naught. Again, if you look at this reaction, there are three chemicals, but only one is gas. The other two are solids. When we are writing out the equilibrium constant of pressures for this kind of reactions, solids and liquids, we don't care. We just look at those gases. There's only one gas here with a coefficient of 1. It's on the product side. Therefore, the equilibrium constant is simply the pressure of this CO2 over P naught to the power of 1. Again, don't worry about solids or liquids. That being said, if the pressure change is huge, we need to worry about the Gibbs energy change of a solid. Let me give you another example. If we convert graphite to diamond at a very high pressure, how high? 100,000 bars. Okay, this is 10 to the power of 5 bars or 10 to the power of 10 pascals. In this case, we need to worry about the change of the Gibbs energy of graphite and diamond when the pressure changes from 1 bar to 100,000 bars. Again, we look at this equation. dG is equal to negative SdT plus VdP. And obviously, you can see G does depend on pressure. It's just the dependence, this dependence V, is much smaller for solids and liquids. However, when the pressure change is very significant, we need to take this into account. When the pressure changes from P0 to P, how does the Gibbs energy change? Well, we just need to integrate this VdP. All right? I'm using P prime here as a dummy variable. And the volume of the solid is roughly constant. So I can take this volume out of the integral. So in the end, this Gibbs energy change is simply the volume of the solid times the change of the pressure. In this example, this P is 100,000 bars, this P0 is 1 bar. So we can actually calculate the equilibrium pressure when there's diamond and the graphite reach equilibrium. When they reach equilibrium, we have this delta G of R being equal to 0. And therefore, this guy, so this is the Gibbs energy of graphite at pressure P. Okay, at pressure P. And this guy is the Gibbs energy of formation of diamond, also at pressure P. When this diamond and graphite reach equilibrium, delta G of R is 0. So this part for graphite is equal to this part for diamond. And then you just need to look up the values of the Gibbs energy of graphite under 1 bar condition, Gibbs energy of formation of diamond under 1 bar condition. I think this is 0. This is roughly 3 kilojoule per mole. And if you know the molar volume of graphite and diamond, plug them in. And this is 0. This is 3 kilojoule per mole. The molar volume of graphite. Okay, I don't quite remember, but I think it's roughly 5 milliliter per mole. And this one is roughly 4 milliliter per mole. Anyway, you plug it in, you will be able to determine the equilibrium pressure when this diamond and graphite reach equilibrium.